Okay, so remember you have a homework. This is about including describe PCA using a language. Yunjian will access your video. You take a short video to explain PCA, and he will score you by the level you think you understand what PCA is. Okay, you probably will see, okay, PCA is a dimensionality reduction technology. Is that true? It's true, yes. People always say that, but it's only partially true because it's one of the applications. So you can use PCA to do the dimensionality reduction, but the PCA analysis itself does not generate the dimension reduction data set. Remember, PCA only change your data points. It only provides the output, a new axis system, new coordinate system. If you have a data set, if you have a new data set, something like this, you have a cloud, and a PCA analysis, the output of the PCA is this 2D, on the center of this and give you two vectors. It's a 2x2, which we want to use this as a new coordinated system to rotate your data and align x-axis because it's principal PC. So for this two-dimensional data set, you can use this as your new x-axis and you project your data onto it. So you reduce two-dimension 2D to 1D, then 2D to 1D. In this case, you ignore the y-axis, and that's your dimension reduction. So if you have a 3D and you found x, y, z, but you only visualize your data, use your x and y in your axis. So you reduce the dimension to 2D. But you still keep the 3D, nothing changed. So PCA is not a dimensionality reduction technology. You just rotate your data and you choose to look at your data, use the top PC, your angle to look at it. Okay, so this had to be very clear in this case. Let's see, today we are going to discuss clustering. I want to first to make you familiar with this notation. Just like if you have a vector, there's two bar here around this vector and square it. What that mean? Yeah, so this is called L2 node. So what is node? Node is if you have the here. Node is the length of this vector. It's the magnitude of this vector. Because L2 node is if this is x, y, is x squared plus y squared. You can take square root of node, and that's the length of this. Okay. So you will see a lot of this symbol in data science literature, papers, articles, and in slightly different form. So if you have the one, So what is this? If you have two vectors, you take the norm of their difference and the other norm. So for example, that's your V1, and then you have another one in Q here. You have two data points, and this format you will see a lot. I believe every single data scientist paper have this kind of form in slightly different format, in reality, it looks very similar. So so this tells you that the length of the distance between these two data points. Okay. When you use this minus this, you get a vector of this and the norm of that L2 norm, that's the distance between these two data points. Why in data science paper you want to have this? Because this compared to data points and found a difference. Your purpose, for example, you want to make the small to make this data points close to each other. For example, we're doing this embedding and we want to minimize the difference between before and after transformation. So you use this. I show you some paper. So we will need this form to our clustering as well, because you want to look at the distance between data points. And this gives you a very quick summary of the difference. It doesn't matter what the dimensionality is, right or high dimension. Okay, so remember this. Yeah, want to find some papers to show you maybe later. Here my screen. Okay, so this is lecture number 6. We will be talking about the clustering. So if you say, okay, I want to do clustering, when you mention this topic to anyone in statistics department, they will shine their eyes because this is the topic that we really like. Many of them probably have their own clustering algorithm developed methods applied to different conditions. So today we focus on single cell data clustering, and we will mention a couple of them. K-means and DB-scan spectrum clustering, and SC3 is sort of assemble clustering algorithm, and we will mention a hierarchy algorithm at the end. So clustering is a typical unsupervised learning method. So what's the input for clustering algorithm? So what do you want to get from this clustering algorithm? What's the input? What do you want to get, or what output we should? The expression for result. Yeah, so input is this spreadsheet like this big X matrix. That's true. That's the only input we need, right? What output you want to get from class whatever? Group ID. Yeah. So you want to get it from a big X, you want to get a vector. This vector contains the membership ID for each cell. Okay, so that's our input and output. Okay, so once you have this membership, okay, you know, cell number 1, 3, 7, 17 is the group 1. So this vector will be the same number of the elements in this vector and the same as the number of genes, cells, right? Okay. So this is another classification. So the difference between classification and the clustering is when you do a classification, you have to give this number and also a label. So, okay, this cluster belongs to this group. For example, cell type. This is called a classification. Well, clustering, you don't have to give what cluster, the name, you just group them. Okay, this group cell belongs to this cluster, this group, not cluster. Okay.
Sometimes we get like the genes which are expressed in two different clusters. So how do we say like this particular gene that belongs to a particular cluster?
You want to see, okay, there one gene
which is
expressed in two separate clusters.
Yes.
Yeah. You know, if you only use one gene to define the property of each cell, then these two group clusters shouldn't be separate, because if you think they all express that particular gene the same. However, because it's a high dimensional data, so the particular gene you look is separated, but the separation is not supported by this particular single gene, it's supported by other genes property.
The clustering will be more based on your specific one, for this choice versus classification will be based on set standards or.
Yes, so the clustering will use all the information of each cells, all the genes expression profile to cluster based on the distance between cells. It only consider just one or two markers. Globally consider all the genes to compare. So in your case, if you have a cell to be separated in two clusters, means globally they look very different from each other, but there are some particular genes, maybe it's shared, still there. But the signal was over-dominated, determined by other genes profile, separated them.
Is there a universal rule like you should have this much amount of the markers for a particular cell type?
I don't think so. Sometimes important gene may be just single markers and people know, okay, there are small clusters. In like small clusters, only uniquely express particular gene. If you have a strong biology knowledge, you probably know, okay, why this particular small clusters there.
So a single gene can define a single cluster?
It's possible, definitely possible, yeah. Depends on your question. Yeah. So we consider this like a per process of your data. Because remember, after the dimension reduction, then you immediately to do this clustering analysis. So this is a per process for the future analysis. We try to automatic to make this process automatic and to help you very quickly get the clustering done. Okay. So I want you to keep on your mind this workflow so you know which step we are in. We are doing
from this dimension reduction jump to this. All right. We're doing this step. You put the cells in different group members, and then, so you can color them. This is a real data set I got from my one of my collaborators in medical school. Well, I don't think this kind of situation is common, but as a small example, I will illustrate the problem with this dimension reduction based clustering analysis, and show you different algorithms and produce different results. The problem with this data is this embedding gave you different density of this distribution of the points. So to us, if you use human eyes to cluster them, you say, okay, this is one group, this is another small group, and this is another group. However, if you use k-means algorithm, you get the cluster like this. This is the original. Then you get yellow as one group, blue, and this teal in another 3 groups. You run the algorithm again, give you another output, similar, but because this random process involved, so they are slightly different membership. For example, this one would belong to this group, was not belong to that group. Yeah.
So if you do cluster, you only care about the distance between the members.
Yeah.
Because if I ask the same group, the distance, yes, this side really because we stay on.
Yeah.
And it forces the other group.
Yeah, that's exactly the problem. So if you use k-means is distance-based. So for the program, for the algorithm, it's only have the distance between cells, between individual cells pairwise. So k-means does not have this global view. Say, I want to stand above the horizon for certain feeds and to look at the global data. So it doesn't have this. So that's why there are some occasions and you get this non-intuitively sound solutions. But numerically, that's from a k-means algorithm. But other approach can do it better. Okay, there are other clustering algorithm can take care of this. And you get the results looks like that. Okay, again, this situation is not common. For this particular sample, because of very poor quality of the preparation of cell, this is from an old mice and the central nervous system neurons, and they thought they are neurons, but could be ostracized. We don't know, and there are degradation of the samples. So you get this uncommon distribution. So real data we process normally have a better clusters per se. So k-means still the one of the commonly used, but I just want to know that there are special cases k-means all work, something like this. Okay. So we can largely separate this clustering approach in different categories: partitioning, hierarchy, model-based, and density-based, graph theory-based. We will look at k-means. I will mention Gaussian mixed model base. We will look at DB scan. Okay. And then their density cluster, the similar as a DB scan, is an improved version of the DB scan. Affinity propagation and the spectrum clustering. Graphic, so network based. So we will mention spectrum clustering at the end of this class. Okay, so here is the k-means algorithm. In the center of this, I want you to look at this. All right. You see the two bars around some difference between data points and the squared. And this expression was summarized together. So if you have I, n difference, so you compute n data points to the central node, okay? And their distance and the squared and the sum together. So what that means here is that particular expression of a paper. Then we will look at, for example, we don't have this group here. So this cluster, we only consider one cluster here. So we will find a C, which called central node, which is in the average in the middle of somewhere here. Okay, this is my central point, this is C. So I have n numbers of cells, and so this is, for example, is my first data I. I will compute the distance from my I to the C. So the expression is like this: xi minus c. Okay, C is also the same data point. Okay. So for the convenience of our, we can keep one of these data point as C. So we consider, okay, this is C. We just compute every other data points to its distance. So what you have done is something like this. So this expression is one of the data points to the C, the distance. And once you finish one, you compute another one. So this I from 1 to n. In total, you have n number of the distance. Okay. So that's an expression of that. This is called the class sum of the square. Which is the distance to the central node. Well, we want to have. So this is only one. So maybe this is called WCSS. So this is only one cluster. If you have another cluster, actually here. We want to have another C. So this is called our C1. Here we have C2. C1.
as WC as is one. We have C2, we will compute number C2, and you get the same kind of expression as 2. Okay. Where all the C2 members to its distance. So for a good clustering algorithm, we want to minimize these values to make them small and possible. Because we want to select the central node, which is located in the center. So on average, I'm close to all my members. Where you find another center close to all other members. You may have another cluster that you have 3 WCSS3 for all number and the distance. At the end, you want to sum all of them. You want to minimize this total. That's our algorithm, the goal, our project, our objective. We want to find the central node, which in the center of my membership, all the members, will the total summation of the distance consider all the clusters to be the minimum. So we want to minimize this. On the way to this. Is that clear? Our objective.
So you're basically creating a networking.
It's kind of networking. Yeah. So you will see this language. Okay. Minimize total square difference. So this is the distance from the point to yourself. Number. That's Euclidean distance because we are considering node level 2. So this is like a description, but you know the idea just like that. Now, if you look at this expression, I hope you can start to recognize this is third arrow, which this is take them and the sum together. All right. This is called an objective function. We essentially want to have a k. We define that we have k numbers. In this case, I have 2 clusters, k equals 2. Then about all this distance to their own number, smaller, and also the total is smallest. Okay, K means you have first to see, okay, how many clusters you want to make. So K, you have to be input. So I said it's unsupervised, but the K is so-called hyperparameter. Okay, it's above to define first how do you structure your algorithm. So you need a K as input. Then the algorithm will put random signal. So it will, for example, put this as C1 and this as C2 first. Okay. From your data, all data points is randomly select 2. Then it start to assign membership. So any data point close to C1 will be my number. Close to C2 will be another number.
cluster, and let's have a compute this. Once it's finished, you move. You change in the synchronous position of the iteration. So the first initial
Yes, with it is. So once you have the membership assigned, then it will re-estimate the cluster center. Okay, at the end, you will achieve this minimization of the achieve to minimize the objective function. So that's a good example. We first have a cluster data like that. We want to have a k equal to 2. Then you randomly assign to central node. Then depends on the distance of the data point to the central node, you group cluster data points into either red or yellow group. Then once you have their member ID, you can see, okay, I will recompute the central node. So after you recompute the central node and this right triangle, and then move into the center of the cluster of the right cluster. Well, this one, yellow one, moved into the center of the yellow one. Okay, then you start again. You start to recompute the membership of all the data points, trade these two new position of the central node as the initial position, and then you recluster the member of this group into red, that group in the red. And then you move the central node again after you compute the new membership. Very quickly, the solution gets converted, stopped. There's no membership change, then you stop your algorithm.
How is it different from PCA?
That's a good question. Well, this is different from PCA. So you can do PCA first to make them look more separable. Then you run the clustering algorithm. They're, I mean, they're not the same technology.
How do you choose the first one?
It's by random number generated, yes. So for very complex data set and where you start from your initial seeding of this central node will have some impact on your outcome. So that's why the algorithm suggests that you can start by randomly choose different initial values of the k node, central nodes, and try multiple times and see whether you get similar results. Okay. It's not too hard, right? So for computer scientists, if you have some coding skills, you probably want to spend 1 or 2 days, you can code this up. You just need to know, okay, how can I assign members of this membership ID, and how can I compute the distance between them, and then do a quick iteration. You just need to know how to keep your vector and the membership vector or to compute the distance. So this is a very small project for computer scientists, for the students. And the algorithm was invented in 1950s, 1957. So to me, it's a relatively new algorithm, not too long time ago. So advantage for this is very computationally effective. So that's why, in my toolbox there, a small rabbit icon in there, and you select how many K you want to have. You just click a button, immediately you get the results. So just costs nothing. Okay, we can use this easily. Okay, Gaussian mixed model. So this is called a model-based. It assumes the distribution of these data points is a combinations of data generated from a normal distribution. In this particular small icon, this is a 2D example. But if I use 1D example, it will be very easy to illustrate the points. So if you know those yellow dots was generated from this Gaussian distribution, and you know where is the mean and how broad this variation is, well, these blue ones you can consider to fit into another distribution which have a narrow standard deviation, and you know where its mean is. So you can easily regenerate some data set look very similar to your observed data. So you basically say, I use two Gaussian distribution to model the data, just like what I described, this height of the man in Italy and Sweden. So you know, if you have that impression, you know how to regenerate a distribution. Well, the clustering algorithm is, you don't have this membership. You don't have any of this membership ID for your data points. You just assume there are two distributions underlying my data sets. And one is close to this center and another close to that center. And try to guess, okay, it's a mixture of the two Gaussian model. Then you fit your estimated parameter with your data and found the maximum likelihood solution. And then you, based on that, you can say, I think this number is most likely to be, this data point is most likely to be in the purple. Well, it's likely to be in here, but very unlikely. It's long tail to here. And that's in the center of this. So you can start to assign the 90% belong to this. Okay, 10% belong to that. Assign the membership like that. Okay. So there's an assumption that the data points follow normal distribution because those ones are easy to compute, to estimate, to fit the data. And you have 2D examples. Yeah.
Do we have to specify K again, just like in K example for the portion?
I think so. I think so. If you say, okay, I have a K3, you probably don't have 1, 2, 3. So limitation for the K-means algorithm and also this Gaussian mixed model, they cannot solve the problem like so-called non-convex shape. go to the non-convex shape. Right? This is a non-convex shape. So on your left side, these are the shape of the data points, the distribution, convex. Well, those are the non-convex. That's why you see this. Okay, the one I just showed you, the k-means doesn't work. That's because the density change greatly. But also this like shape. If you have a shape like this, two clusters, because it's a non-convex shape, and k-means will cluster as this like a central node here for the right, and then another central node for blue here, right? That's expected because of that property. It's okay to cluster a sample like this, is fine, but definitely will not work in this case. Will not work in this case because they are non-convex condition. Is that okay? Yeah. So we need to have some solutions for the density-based method to take care of those density change, because if you have a cluster as is sparse data and the distance is so large, where another small cluster's distance is so small, you have a great contrast between those two. K-means doesn't work probably. So this is a density-based spatial clustering application. It's even newer. Okay, the method published in 1996. So in this case, they look at a lot of hyperparameters first, and to define small cluster calls, and then to look at outliers and see whether another neighbor point should be joined this or not. So I'm going to play this video to let this video to explain.
Hello and welcome. We'll be covering DB-Scan, a density-based clustering algorithm, which is appropriate to use when examining spatial data. So let's get started. Most of the traditional clustering techniques, such as k-means, hierarchical, and fuzzy clustering, can be used to group data in an unsupervised way. However, when applied to tasks with arbitrary shaped clusters or clusters within clusters, traditional techniques might not be able to achieve good results. That is, elements in the same cluster might not share enough similarity, or the performance may be poor. Additionally, while partitioning-based algorithms such as k-means may be easy to understand and implement in practice, the algorithm has no notion of outliers. That is, all points are assigned to a cluster, even if they do not belong in any. In the domain of anomaly detection, this causes problems, as anomalous points will be assigned to the same cluster as normal data points. The anomalous points pull the cluster centroid towards them, making it harder to classify them as anomalous points. In contrast, density-based clustering locates regions of high density that are separated from one another by regions of low density. Density in this context is defined as the number of points within a specified radius. A specific and very popular type of density-based clustering is DB-Scan. DB-SCAN is particularly effective for tasks like class identification on a spatial context. The wonderful attribute of the DB-SCAN algorithm is that it can find out any arbitrary shaped cluster without getting affected by noise. For example, this map shows the location of weather stations in Canada. DB-SCAN can be used here to find the group of stations which show the same weather condition. As you can see, it not only finds different arbitrary shaped clusters, it can find the denser part of data-centered samples by ignoring less dense areas or noises. Now, let's look at this clustering algorithm to see how it works. DB-SCAN stands for density-based spatial clustering of applications with noise. This technique is one of the most common clustering algorithms, which works based on density of object. DB-SCAN works on the idea that if a particular point belongs to a cluster, it should be near to lots of other points in that cluster. It works based on two parameters, radius and minimum points. R determines a specified radius that, if it includes enough points within it, we call it a dense area. M determines the minimum number of data points we want in a neighborhood to define the cluster. Let's define radius as 2 units. For the sake of simplicity, assume it as radius of 2 centimeters around the point of interest. Also, let's set the minimum point, or M, to be 6 points, including the point of interest. To see how DB-SCAN works, we have to determine the type of points. Each point in our data set can be either a core, border, or outlier point. Don't worry, I'll explain what these points are in a moment. But the whole idea behind the DB-SCAN algorithm is to visit each point and find its type first. Then we group points as clusters based on their types. Let's pick a point randomly. First, we check to see whether it's a core data point. So, what is a core point? A data point is a core point if, within our neighborhood of the point, there are at least m points. For example, as there are 6 points in the 2 centimeter neighbor of the red point, we mark this point as a core point. Okay, what happens if it's not a core point? Let's look at another point. Is this point a core point? No. As you can see, there are only 5 points in this neighborhood, including the yellow point. So what kind of point is this one? In fact, it is a border point. What is a border point? A data point is a border point if A, its neighborhood contains less than m data points, or B, it is reachable from some core point. Here, reachability means it is within our distance from a core point. It means that even though the yellow point is within the 2 centimeter neighborhood of the red point, it is not by itself a core point because it does not have at least 6 points in its neighborhood. We continue with the next point. As you can see, it is also a core point. And all points around it, which are not core points, are border points. Next core point, and next core point. Let's pick this point. You can see it is not a core point, nor is it a border point. So we label it as an outlier. What is an outlier? An outlier is a point that is not a core point and also is not close enough to be reachable from a core point. We continue and visit all the points in the data set and label them as either core, border, or outlier. The next step is to connect core points that are neighbors and put them in the same cluster. So a cluster is formed as at least one core point plus all reachable core points plus all their borders. It simply shapes all the clusters and finds outliers as well. Let's review this one more time to see why DB-SCAN is cool. DB-SCAN can find arbitrarily shaped clusters. It can even find a cluster completely surrounded by a different cluster. dbScan has a notion of noise and is robust to outliers. On top of that, dbScan makes it very practical for use in many real-world problems because it does not require one to specify the number of clusters, such as K in K-means. This concludes this video. Thanks for watching.
Is that simple? Yeah, it's just very physically, intuitively, but it's very simple, right? This is just like a worm to move from one position to another to look at the neighbor. Yeah, what's your question? No, yeah. But I don't agree with the last sentence, this video talking
Sentence.
about.
Means.
So it says you don't have to specify how many clusters you have to give, but you still have to give two parameters in order to define this algorithm. So you need to give R, which the radius of the unit, and also you have to give M, how many members in that cluster required to be a center. So you don't give number K, but you give another two hyperparameters. I don't think this is a advantage for this algorithm compete with the K-means. There's another but you can take the similar and the video explain this idea. Okay. So that's a limitation for dbScan. It's sensitive to the initial values of this R and M. So if you give different R value and different M, you get different results. So the next paper try to solve this by a data-driven way instead of you have an initial guess and what's the radius would be, what numbers of membership has to be in the core area. So this algorithm, the extension of a dbScan algorithm to try to solve this by just look at the data itself to define this hyperparameters. So this algorithm consider local density rho here, and also this third one. Compute minimum distance between data points. So it's computed two additional parameters from the data. So it's still unsupervised, but you learn from the data itself to separate the data points based on these two parameters. And they try to find those outliers here. And then use this information to define, okay, we should have a how to help your dbScan algorithm basically. Okay. So I will leave this for your own to read if you like this paper to see, okay? Because this is very simple. There's no mathematics getting involved. So also only the distance, the density, the radius, and the member categories. Okay, so it's relatively easy, but I think if you like to just read this. So in last semester, I assigned a homework like you to read the paper and then explain some ideas behind I'm thinking something else this semester, so I will see whether we should make this as a homework or not. But if you like, just spend some time, follow the link and read the paper. Okay, graph theory, should we take 5 minutes break, come back? 3:11. Say about data. Yeah, that's your own data. Yeah. Okay. So yeah. That's the NPC, the liver non-parallel come out. Yeah. So I think yeah, and in the beginning I used a 10 units to cluster, but only to annotate the automatic analysis and two-step. But I choose I think this one. Yeah. And the first one, step. Yeah. I can get, nobody can get, this setup. But the problem right now, I have is that I have some marker, for example, this cell tab. I detect the, this gene. Yeah. This gene is the colonial cell. So it should be in this group, but right now they automatically happens. Yeah, so you can rename it. So the other rename it, just click this button. Rename cell type. I can choose the height size. Yeah. But we have two, I think we have two cells. We just rename it. Okay. So how? Yeah, you want to rename it. Log inside. So, and yeah, you should maybe, yeah, it's already changed. Definitely, I think there's some program for you. Yeah. This will be another side. Yeah, so how you can see, I want to make a new cluster. A new cluster. So now it's called cluster 11. I don't know. I have to figure out whether the cell type has already been included. I think the cell type has not been given to that cluster. Yeah, I can help to change a little bit. Maybe to assign a cell type. So there is no way assign cell type for many. Yeah, not automatic. Yes, that will be you have to involve in as a you export this to the MATLAB and also change it manually. I will show you how to do it, but yeah, you can do it. Yes. Okay. Yeah, but not through the interface right now. So I know what your problem is. Yeah, I can make that happen. So select this and make a new cell type, something like that. Yeah, the good thing is that through this we can separate the cell types that we need. Yeah. So because I look at we have cell markers. Yeah. Yeah. That's very cool data. I know it's, yeah.
Is there a way to see the topic genes or the genes in this one cluster?
Yeah, probably I will show you Thursday, so you highlight this and select marker genes. And top 10, for example. You will compute and give you top 10. Okay, for macrophages.
So, by the way, I will, I think you'll do this to.
Yeah, we can set up a meeting, yes, yeah.
So we have, that's the agent. Agent.
Some of the highly specific. You look at, yeah. But you have a top 50.
It's okay, right? Thank you.
Okay. Yeah.
Oh, I know that you remember something about
Yeah. Yeah.
Generally, this is about the bulk. But as I know, if it's about the listening with audience, then you will feel that.
Just few dots.
Yeah,
It's-
so possibly.
doesn't make any sense. PCA should be. PCA should. be.
Because I think that example, wait, but she said, oh, you can try saying project.
Yeah, you can, of course, you just treat like you only have 7 cells. For example, I don't know how many samples you have for your
We
archive.
have wild type and non each number 3, so even if it's a 3 dots.
Yeah.
Just
Make no sense.
So this is the result that humans including if possible with orange, but we cannot get a different word with all from orange.
No, if you only have 6 data points, then you have 6.
What I thought with the orange so far is PCA, volcano and FitLab and like pathway analysis.
Yeah,
Could we do also like gene to gene contribution?
there's no way because the sample size is not enough. Yeah, single cell is okay because each sample is sort of cells. But in bulk RNA, we just don't, it's not enough. Any correlation between any genes, no way to establish. That's right, yeah, it's.
I'm going through the shed, but I'm going through this. Yes.
अगर हम लोग सेल सबसेट करेंगे तब क्लासिफिकेशन होगा बट समझ तो रियलाइज जैसे वो चीज़ें डेटा करना पड़ेगा, सारा डेटा जैसे पूरी क्लास का डेटा करना पड़ेगा, फर्स्ट
Okay, so this old professor is MIT professor mathematics. He's famous in teaching lineage algebra, and when you transform graph into a matrix, then a lot of lineage algebra algorithm can apply to the matrix or vectors, then solve the problem in the graph. It's very cool, and the graph theory and using the matrix multiplication, decomposition, transformation, etc., to learn the graph. So with this large graph, you can start to use graph theory to identify the modules, or sometimes called subgraph or communities. So if you have a cells and you do this dimension reduction, project them on the low dimension and start to build the distance matrix, and then you can create this graph. Then all this graph-based analysis method you can apply to there. The one I'm going to introduce this is called spectrum clustering. So this algorithm apply to all kinds of conditions of you have data points distributed like this. Okay, so k-means also will work in this case. K-means only work in these two cases, but the spectrum clustering works fine. That case is fine. So I'm going to use a small example to illustrate the steps in the spectrum clustering algorithm. Let's see. I don't think we have time to illustrate anything on the board. So I just highlight what we have on the slides here. For example, you have 6 cells and their distance you can measure. Okay, each cell is just a vector, so you can take the difference and take a norm and square. So you can compute the distance, then you can link them. And then you can set up a cutoff. See, okay, 3 and 5 too far away, so this, we consider them not linked. So you can set a cutoff. See, I want to keep the minimum distance, the largest distance between connected cells to be 0.54, whatever numbers you come up with this graph. And you can represent this graph with this adjacency matrix, which if you have 1 means 1 and 2 nodes with 2 cells are connected. 1 and 4 is not connected. The 1 from 1 to 4 is 0. Okay, so basically you map your graph into a matrix. This matrix is symmetric if you don't consider the direction. So from 1 to 5 and 5 to 1 are the same. So position 1, 5 is 1, 5, 1 is 1, the same, no direction. You can have directed graph if you only consider from 1 to 5, so you put 1 here, but not from 5 to 1, so put a 0 here. Otherwise, you have a symmetric. You can have weighted. Rather than put 1 here, 1, 0, you can put how strong the connection is. So if 1 and 2 is strongly connected, you put a larger number here, 1.5, for example. If 1 and 5 is loosely connected, you put 0.2, a small value here. All right. So in this case, we use unweighted, undirected symmetric network. So you have this adjacent matrix. Then you can compute a degree matrix. When we talk about the degree for the nodes in the network, we mean how many connected partners for each node. So the degree for node number 1 is 3 because it has 3 connections with other nodes. The degree for node number 2 is 2 because you have 2 connected members. Degree for 3 is 3. So how can you compute the degree? If you have adjacency matrix, you can take the sum of each column. So for node number 1, you have 1, 2, 3 connected ones. So the degree is 3. So you sum the column. For number 2, you have 1, 2 connected numbers, so the degree is 2. So from adjacency matrix, you can very quickly compute the degree matrix and put their degree in this diagonal position and put all the zeros in all other places. So now we have 2 matrices, A and D. A is network itself. D is a degree for each node, which number of degree is in the diagonal position of this matrix. Now we are going to compute a matrix called the Laplacian matrix, L. L is the difference between 2 matrices. So you have a degree matrix minus adjacency matrix. So D minus A. In adjacency matrix, diagonal position are zeros because you are not supposed to connect to yourself. There's no self loop. So in the adjacent matrix, diagonal position are zeros. Well, in degree matrix, you have all the degree, the positive values for each node. So the difference between them will be still the degree matrix. Well, the other positions are negative ones because you have degree matrix of all zeros, negative minus all the ones in the adjacency matrix. So this is a Laplacian matrix. So this matrix is very useful for downstream operations using lineage algebra applied to matrix. It contains information of the structure of the network, and also for each node, their properties in terms of connectivity of this node to other nodes is in the diagonal position. So this is an information rich matrix. So we are going to do something with the Laplacian matrix here. So for spectrum clustering, we have this Laplacian matrix, and the next step is to do this eigendecomposition. You found the eigenvalues and their corresponding eigenvectors. And then you found, you extract the second smallest eigenvalue and its corresponding eigenvector. Okay, you see this eigenvalue, you have 5, 4, 3, and this is the second smallest. Its corresponding eigenvector is this. Okay, so we extract this out and use the parameters in this column to separate data points based on their property. Okay, So in this small example, this column corresponding to 3 positive values and 3 negative values. This tells us we can separate these 6 data points into 2 groups by their sign, basically. Positive is one group, negative another group. So that's the cluster. So you have a network, you have a graph, and then the spectrum clustering through these steps tells you, okay, we should separate the network into 2, one by in the middle of this. 1, 2, 3 should be one, and the 4, 5, 6 should be another. So that's what our cluster separation. Is that okay? So this is very simple steps, right? And this procedure also applies to a weighted network. Remember, we had this small example as unweighted. So that's why you have 0, 1 in there. It's connected nodes and have a 1 link between them. But you can have weight in there. So from 1 to 5 is 0.1, and from 1 to 2, 0.8. So you have a not a binary matrix or adjacent matrix, but it's weighted. And still, you can compute adjacent matrix. So that's adjacent matrix. It's not computed from the graph, right? You can still compute the degree matrix. You do the same thing, you sum the columns. And then you get a degree matrix. Now it's not an integer anymore, it's weight. And then you can still compute Laplacian matrix, same equation. Yeah.
The 0.8 from 0.1 to 0.2.
Yeah, so this is given by the network itself. So there are different ways you can create weighted network. For example, in our case, single cell, it could be the distance. You measure the distance between cells. Maybe 1 minus distance because it's smaller. The larger, the stronger connection is. So we just assume we already given this network. We can represent this network using adjacent matrix. So that's the input for the clustering, spectrum clustering. I think your question was ask me, how can we convert this data matrix X into a network? Yeah. But here I'm just showing you, once you have a network of your data points, and what to do next. We do have a lecture with talking about how to create the networks. Yeah. There are KNN, the K nearest neighbor networks. We will discuss the network construction next. So here is the clustering is based on you have the network of your cells, and then you can do this clustering. So same steps. D minus W. Okay, it was A is adjacent matrix, but now I replace with a W. W is a weighted adjacent matrix. The same thing, you get a Laplacian matrix. And then you do eigen decomposition on this squared matrix and also symmetric. So you have this solution. And then you found the second smallest eigenvalue. And there is corresponding eigenvectors, which is this column. The first one is not informative, it's all the same. The second one is contain the information of the separation of the modules, the first separation of the modules. I don't know who figured out this algorithm, but it just works with this Laplacian matrix to do this eigen decomposition. It's really cool. It works. I still have trouble to figure out why it works. I don't know. I just know, okay, Laplacian matrix contains the structure information of your connectivity between your data points, contain the information of each data point's weight. Yeah, but that's a procedure. If any one of you found out why it works, let me know. I want to know the intuition and what's the explanation of this. So again, once you extract those eigenvectors corresponding to the smallest eigenvalues, you start to use this as a new coordinate system, as your new data point to separate the nodes in the network. It's very easy to separate them. In this case, the first three and the second, the last three are the two separate groups. In this small example, it's very simple. You cluster them into two groups, but in more complex situation, you have more complex solution here. So you can use this coordinates as input for your k-means to separate these data points into clusters.
So they have just used eigen decomposition as the dimension reduction.
I think so. There's some kind of a dimension reduction, and to reduce, for example, this high dimensional matrix, because your every node, every data point is defined by all their neighbor relationship with others. So if you treat this rows as your data points, and the columns, those are the variables to define each of the nodes. And then eigen decomposition, then I don't know how this eigen decomposition learned. I have trouble.
The PCA also can just take the first two things for confidence and here also can eigen decomposition first two.
Yeah, in PCA, you take the largest
Yeah.
eigenvector, which is another spectrum, other side. But here you take the smallest eigenvector, eigenvalues, and its corresponding eigenvectors. Yeah, I have some thought which not linked on my mind why it works. Yeah. But the PCA is not running on the Laplacian matrix, on the covariance matrix to do eigen decomposition. But here is this Laplacian matrix and eigen decomposition. I hope someone can explain to me the geometric understanding of this. I haven't found any good tutorial to explain this clear to me. But I believe the first one who discovered this will be really happy because that's very cool. Yeah. Anyway, we are going to try all these Thursday in MATLAB computer, you try with your own data. Yeah. Yeah, so that will be, for example, if we have, I don't know, I still have this data set. But if you use k-means to do this, that's a solution. If you use spectrum cluster algorithm, again, another built-in function in MATLAB toolbox, you get this solution. As I said, clustering, spectrum clustering apply to many different conditions. Yeah. So another example, spectrum clustering is this algorithm in the middle here, this column. I think this study tests several different algorithms like DB scans here. Okay, for different data set with data points arranged in different shapes. So it's worked fine in all the conditions like this. DB scan is also okay. There are other k-means, basically the k-means. In the early, so this is a blog page, is a little bit out of the date. They compare k-means and DB scan and another hierarchy-based clustering on the real data sets, found a different solution, different results. Okay. There's some papers just compare different algorithms in so we are going to mention SC3. Okay, so their evaluation paper systemically evaluate different algorithms, and they set up some of this golden standard. So okay, they believe this way to cluster your cells is the best solution. So compared to other the output of algorithms, which one gave you the best answer? There's an idea is to use different algorithms and combine their predictions and to vote. Okay, see, if you use 10 different algorithms, 9 of them believe cell 1 and 2 should be in the same cluster, then you just assemble this information to do it. So this is a very common technique. As I showed you last week, there are dimensionality reduction technique, and this assemble method try to synthesize all the dimension reduction algorithm generated results to give you the so-called meta dimension reduction results. So this is an illustration of how to do it, but still there are many problems with this procedure. Which one you want to select to include in your assembly clustering algorithm, and how are you going to combine them? They all are topics that people have to think about this when you create something like that. Okay, so I'm going to explain SC3. So this is a name of algorithm. So this method is different from what we have with k-means or others. It's specifically designed for single cell data. So all the other methods apply to to the data set already finished the dimensionality reduction. So in my toolbox, there's the one with a lot of branch tree branches. Let me show you. Okay, to do the clustering, and so you see here, and I don't know if you can see this in this small suggested the function. So this is called a clustering using embedding S. So the algorithm here, like k-means, and also another one, it's based on the position of all the cells. As well, this one here is clustering using expression matrix. X. So this will not rely on the position of the cells already generated by the dimensionality reduction algorithm. So the input for k-means is only the position of each cell here. Well, this one is not. This button runs SC3 basically. So SC3 start with your X matrix. It will first get rid of some lowly expressed genes. Okay, just like a QC, there are some genes expression level abundance is too low. It's only present in less than 5% of cells, so we have to filter them out. So filter them out, the good genes out and include it in the downstream. So this is the first one. And then start to compute a distance matrix. The algorithm computes 3 distance matrices. One is Euclidean distance between cells. So this matrix, the green one, is a squared matrix, cell by cell. So in our example, if you have 2,000 cells, so this will be 2,000 cell by 2,000 cell, and the distance between each cells. So that's matrix 1. Another matrix is so-called Pearson correlation matrix. It will compute all the gene expression profile of the 2 cells by looking at its correlation coefficient. So you get another distance matrix, and then Spearman, it's the same correlation coefficient matrix between cells. Okay, so now this big X matrix has been converted into 3 squared matrix, 3 distance matrix, cell by cell. So next, for each of these distance matrix, there are 2 transformations. One is a PCA, one is Laplacian transformation. Okay, you know PCA, and you know how to compute the Laplacian matrix. So each of these 3 distance matrix was transformed in 2 different ways. So you get 6 in total transformed matrix. Okay, now the X matrix become 6 big matrices. And for each of these matrix, we will do select different ranges of the variables. Okay, now we consider X, the rows as a number of cells, the cells, well, the columns as variables. Now we are using like 5 variables to define cells. We use 10 variables to define cells, and look 20. So you select a different range of these numbers of variables to define your cells. And you apply this to each of these transformed matrices. And you use this to do K-means algorithm, basically. Okay. Because you have all the cells, you have their variables to define the cells. And then you can run the K-means for each of these subsection of the extract columns. Okay, now if you have 6 matrices, and for each 6 matrices, you found 5 different ranges of this. And you can make 30 basically as a matrices as input. So you create 30 K-means algorithm to class the cells. And once you finish that, you get the consensus. Okay, these 2 cells always being clustered in the same cluster, and they put in the a cluster. And at the end, you get your final solution. Okay, so this procedure has no dimensionality reduction. It's not rely on pre-traded cell positions, because otherwise you will be biased because which algorithm you use to embedding those cells. But here is try to take all the spectrum of the cell similarities defined in different ways. Try to get this from different sections of the understanding of the cell-cell relationship, and you cluster them and take average of consensus. It's not elegant. It's just run. It's time consuming, so that's why you need to be careful, and it will take some time. And the result will be slightly different from what you do the dimension reduction first, then cluster them. So it's really, if you do the dimensionality reduction first and then cluster later, the quality of the dimension reduction will impact your downstream clustering results. Okay. So if you have 2 cell types, they're supposed to be subtypes, but the t-SNE tend to put them together. Then you downstream, you will never be able to separate them, because your K-means you'll rely on your embedding position of your cells. But here, there's possibility to learn from one of the steps, which this could be the separated 2 subclusters. So if I run this, if I run SC3, use expression matrix as my input, the membership will not be the same as their 3D embedding positions. Some, for example, this position, this cell could be in the same membership with some cell in here. Okay, some kind of inconsistent will be here. That's because the dimension reduction lost some information from there. But largely, they should be consistent. If you have a clear separation of different cell types, you should get a very consistent results.
So we have a spectral clustering, I can see, it will like pretty similar, but both of them are not yet.
Spectrum clustering will still be in this group. In this, using, I can put a spectrum clustering here. It's also used as embedding the position of the cell after dimension reduction.
So is this.
Same as the k-means. Oh, you mean this one?
I mean, in spectral clustering, it is not using a Disney or UMAP, it's just taking it from the application.
Oh, so you mean the spectrum clustering?
Yeah.
I haven't tried spectrum clustering directly onto X matrix. Yeah, we can give it a try and see what we get.
Well, I think the one that Seurat uses, the Lowen algorithm, is just, it uses the similar, it makes adjacency matrix and then it goes on do the similar thing based on probability reduction.
Based on the dimension reduction, based on this position of cells?
No,
No.
it uses the definition matrix and it's based on
Network.
probability reduction.
Okay.
It's based on network. So I was just wondering if this consensus clustering is similar, will produce similar results as network as we use during spectral clustering. That is also not reliant on.
I believe in different algorithms in large, they should be largely consistent to each other. There's subtle difference, maybe very important biologically. So we need to pay attention to those differences sometimes. Shran is describing a Seurat package and they use graph-based analysis first to build a cell networks. For example, I can build cell networks using KNN network. So if I click this, you will see, okay, there all the cells will be connected based on their neighborhood distance, and then you can do some community detection applied to this graph. Yeah. So Shran would describe this Seurat package use this method. But in largely should be consistent with all this. Okay. If you want to look at the SC3 algorithm, there are R package, and that's my implementation in MATLAB. So MATLAB can do this every step very easily. So it won't take me too long to code this to reproduce the whole SC3 algorithm. But for you, it just be clear that you can do clustering directly from the X matrix, or you can do the embedding first, and then look at the position of the cells to cluster cells. Okay. You should be similar. Yeah. Yeah, so the last class of the algorithm is to do this hierarchy algorithm. Basically, it's slightly different from this k-means, which k-means are called a partitioning algorithm. Those ones are to build a trees. Look at the similarity between cells and build a tree. Similars will be in the same sub-branch. The larger group of the algorithm that's in the molecular evolution, people build the trees all the time. They build NJ tree, neighbor join tree, maximum likelihood tree to do this gene tree or species tree. And there's a large group of the molecular evolution people working on that area. We can use this dendrogram algorithm very easily and to build those trees. And you can use this way to find outliers, for example. There are packages to do this. It's not very popular because once you have a large number of cells, the tree representation for the cells relationship gets really resource demanding. You need a large memory to represent this tree structure in the memory of computer. It was possible at the early stage of the single cell data, but nowadays we don't use this tree-based clustering algorithm anymore. Too slow. Okay. Another example that which year? This is 2016 publication. Use this hierarchy clustering cluster cells. Okay, that's all for today. Any questions? Homework questions? What? Good. Okay, so Thursday we will play with this clustering algorithms, okay, on computer.